So last time we have discussed the some general properties of eigenstates and eigenenergies of this hydrogen atom, right? So we know that the Hamiltonian of the system has a very special form. Okay. Of course, it's it contains this kinetic energy, and then you have this wonderful R potential, right? So this is the Hamiltonian of this one, and this one we can write into a dimensionless form. Okay, so that can be written as okay. So with units, this one is called a readable energy. Okay, that's about a 3.6 eV. Okay, and then the length scale is called Bohr radius. That's about a 0.53 angstrom. Okay. Well, so this is the one thing that we have learned, right? And then the states can be written as the radial part, and then times the angular part. This is the azimuth angle and also the polar angle. Right. And this one actually is proportional to the spherical harmonics, right? And this RMR is the radial part. So in general, it can be written as R to the power L. Okay, so that means if L is not 0, it's going to be 0, and actually L is order 0 at R equals 0, and then you have 1 plus A1R plus until the last term is M minus L minus 1. Okay. Right. And then you have exponential function. E to minus R divided by R, okay? And the quantum numbers, this M equals to 1, 2, 3, all different quantum numbers. And L actually is limited to, at the most, to M minus 1, okay? From 0 to M minus 1. So this is the angular momentum, okay? So L squared equals to L times L plus 1 and h bar squared. And the energy is determined by this principal quantum number, okay? Right, so this one is only for 1 of R, minus 1 of R potential, okay? So that's a special case. For general central force problem, so the energy should depends on not only the principal quantum number, but also on the angular quantum number, okay? So that is the special case of this one, okay? Right. And then M equals to 0 plus minus 1 until you have a plus minus L, okay? So this actually is the quantum number for the Z component of the angular momentum. So LC equals to M times h bar, okay? Right, so if we count the number of states, so immediately you obtain this, for this 1 of R potential, you have this degeneracy equals to 1 plus 3 and then plus 2m minus 1, that equals to n squared, okay? So if you take spin, if spin is counted, it will be d equals to 2 times m squared, okay? So we will talk about the spin a little bit later. Right. So that is the very quick summary of the states and the energy of this hydrogen atom problem, right? Okay, so now today we're going to try to have a more close look of those states, okay, and try to get more familiar with this wave functions, okay. So since understanding of this, the shapes and some features of this eigenstates of hydrogen atom actually is very important for understanding the chemistry, for understanding the solid-state physics, for understanding molecular structures, right, and so on and so forth, okay, in physics and in chemistry, okay, right. So let's start from the simplest case, the hydrogen atom S states, okay. So let's consider the case that so so-called S states. So S states all have this L equals to 0. So that means L squared equals to 0 times h bar squared, and LC of course is also 0 times h bar, right? Okay, so that means the degeneracy D equals to 1, okay, or 2 if spin is counted. Okay. Right. So now we can have, for example, we can have 1s, that is a state that n equal to 1, L equal to 0, and m equal to 0, right? Or 2s is n equal to 1, L equal to 0, yes, m equal to 0. And 3s is n equal to 1, L equal to 0, and m equal to 0. You can continue this one, right? So you can have any S states. So these S states, of course, you have first 4. So the angular part is 0, 0, theta phi. So this one is just a constant, right? Oh, sorry. This is 2. This is 3. Sorry. Thank you. Yeah. So it's a yeah. So the angular part is a constant, right? So the wave function, you can say that the wave function per se m L m. So that will be simply just proportional to m and 0 r, right? So that's very simple, okay. And we can take a look of different states first, and then basically that means the wave function has rotational invariance. That means if you look at this wave function, actually it's the same for any angle, right? So then you can just take a look of the wave function along the radial parts, okay? So let's look at the radial parts. This actually is very simple, right? So let's look at this R10 first. And this one actually is proportional to e to minus r. Okay, of course, in the dimensionless coordinates. If you want, you can put AB right here, but we just write this one as dimensionless. Okay. So that means you take AB, the bore radius, as a unit. And this one, of course, if you write this one as a function of r, okay, so it's going to be some function like this. Okay, so it decays, and so the decay length is about the length scale is about the bore radius, right? Or if we want to go to this side, so this will go like this, right? Suppose you put it on the x-axis. If you put this as x, for example, and this is negative. So you can see that this wave function is not like smooth at I equal to 0. Okay, that is because of the potential r. The potential 1 of r is infinite. Okay, at this one. Okay, so this is so this part, and then you can also look at the probability of finding the particle, the electron, at a distance from r to times from r to r plus dr, right? So that would be r squared so 10, sorry, let's put 10 right here, squared r and dr, right? So you can see that so the most probable position actually is not r equals 0, even though the wave function has maximal at r equals 0, but because the shell has a very small volume at r equals 0, and then when the radius is increasing, the shell volume is increasing. So you actually have the most probable. Okay, so this one is PR, right? So you can see that this is the most probable distance. Okay, right. And people often use the so-called electron cloud, okay, and to plot the wave function, the probability density, right? So if you have the nucleus right here, actually it's something like this one, right? Okay, so that give us the distribution of. So it gives us a kind of a picture illustration of the probability of finding the electron at different. So this is a nucleus. So nucleus right here, okay, right. So that is the 1s state electron core, okay. So you can see if you plot this one to this one, so the wave function actually goes like this. Okay, right. So this is the 1s state. Okay, so it has spherical symmetry, and so in this sense, we say that because of this rotation invariance, we say that the s states, looks like a scalar. Okay, and a scalar has only one component. Right, for example, mass, charge, okay, kinetic energy, and so on and so forth. Okay, so this is one property, and the second property is invariant on the rotation. So if I have a charge, for example, you do a rotation of the space, the charge will not be changed, right? If I have a mass, and the charge will not be, the mass will not be changed if you do a rotation, right? And also to describe this physical quantity, mass, you only need this one quantity, okay? And the S state, of course, is a wave function, okay? And this sense, but you have only one state. For each shell, you have only one state. So in this sense, we say we have only one component. And this component actually is invariant on the rotation, okay? So this is the case for the 1s. And then you can also consider the 2s states. And the 2s, now the wave function goes like this one. It's still maximal at this, but has one nose, then goes like this one. So this is R20 R. Okay, of course you can also plot the probability of finding the particle, the electron at the distance R to R plus dr. So that one will be, now you can see that something goes like this one, right? Okay, so this is PR that equals to R squared and R20 R. And if you look at this wave function, it actually goes like this one. So it's it has a maximal inside, right? Okay, but then there's one radius, so you have at this radius, the wave function equal to 0, right? And the outside, okay, right? So the point is that so this is the surface corresponding to this one. So this is the surface. So well, the PHYS 200 equal to 0, right? So we call this one the node surface. Okay. So the number of the node surface equals to what? Equals to 1, right? So you can go back to the y state. If you look at this, the number of node surface equals to 0, right? Okay. So this is a feature of this 1s 12 states, and later we're going to see more such kind of properties. So try to keep the number of node surfaces, okay, when you look at the state. So this is the 2s state. So it also has a spherical symmetry. That means the wave function is invariant on the rotation. So it's like a scalar. And all the s states actually are like scalar, okay? And then let's look at the 3s states. Okay, now you have 3, 0, R, right? So that will be something like this. And the wave function, of course, it goes like this, and then you can say there will be 2 nodes, right? So, and again, so the probability of finding an electron at a distance from R to R plus dr will be something like this one. Okay, so this is a PR equals to R squared, R30 R squared, right? Okay, so that is the, and then the probability of finding the distance, and then you plot the wave function, and there will be 2 nodes, right, corresponding to say this one, and then okay, and this one. So inside is something like this one. So the phase is positive, and this one okay, the phase is negative, and outside again, right? Okay, so if you look at the phase, so you have, first of all, you have a number of node surface equal to 2, right? And then the phase, look at this phase. So this one is positive, and this one is negative, and this one is positive. Okay, so the phase of the wave function PHYS change sign twice, right? That's because every time when you cross a node surface, the wave function will change the sign. Okay, so PHYS change the sign. You know, crossing a node surface. Right. Of course, you can continue this one to the 4s. Okay. So I will not do that one. So I leave it to you to consider those things. Okay. And then you may ask a question. So you can see that m increase the number of the node surface. increase, right? So actually, it actually equals to m minus 1. Okay, in this case. So why? Okay. So I will not answer this question at this point. So let's examine more cases. Look at the p states and the d states. Furthermore, and then we can have more discussion on this kind of number of normal surfaces. Okay. All right. Okay, so now let's consider p states. That's slightly more interesting, okay, because the x states is just boring, it's just rotational symmetric, symmetric. So it's invariant on rotations. And the p states has an L equals to 1. So now m can equal to 0 or plus minus 1. So you have 3 components. And so you may wonder, are these 3 components full vector? Okay, so we're going to see, okay. So p states, and then if you look at the wave function, the angular part, okay. So the angular part, that is y L m theta phi. So this one equals to basically p 1 m cosine theta, right? And e to I m phi. So it's a complex number. It's a complex function. Okay, it's not very convenient to be shown in the xy plane, right? In the 3-dimensional space. Okay, so you know that it's already very difficult to show the wave function in the 3-dimensional space. And then what we can do if it's a complex number, okay? So but remember, if you look at this one, if you look at the L1 plus 1 theta phi, so this actually equals to L1 minus 1 theta phi, take the complex conjugate. So that means these 2 states actually are complex conjugate to each other. So then we can use these 2 to form new states. So we can say if we consider the state as the real part of this one. And this one, of course, just equals to divided by 2, right? Okay. And if we want to make this one to be normalized, so we wish one to put this one as square root of 2 like this one. Okay. Right. So that's the real part. Okay. And then you can also consider imaginary part. Okay. So that will equals to square root of y1 plus 1 minus y minus 1. Sorry, there's no complex conjugate right here. Sorry. Okay. Right, something like this one. Okay. So these 2 states, we can call this one px and py. So y is called x and y. Okay, later it will be clear. Okay, we call them px, py. First of all, and this px and py, they are orthonormal. That means you have px, py equals 0, and px equals to 1. and py equal to 1. Okay, you can check this. So that's one thing. Secondly, if we put this one acting on this px, okay, you can see that this is just basically equals to 1 plus 1 plus 1 minus 1 divided by square root of 2, right? But since both of this one are the eigenstates of L squared, so you can find that this is basically n squared 1 plus 1 and plus L squared 1 minus 1. Okay. And this one, of course, we just equals to 1 times 1 plus 1 times h bar squared, and then times px. Okay. And similarly, you also have this py that equals to L times L plus 1 and py, okay, times h bar squared, okay, right, with of course L equals to 1, okay. So for these two, so you know that so px, py, they are eigenstates of L squared, okay. And then how about LZ? So let's check this, say 1 plus 1 plus 1 minus 1, right? So now this one equals to, the first one will give you h bar 1 plus 1, but the next one will give you minus h bar 1 minus 1, okay? So that means LZ acting on px actually will equals to I times py, right? So similarly, you have LZ and py will equals to minus I px. I leave this one for you to check. So that means these two are not eigenstates of LZ, okay? Right. But anyway, we can still got a lot of information about this, px, py states, okay? Of course, you may wonder, how about the zero state? And the zero state is okay. The zero state, remember this zero state, that equals just PL0 cosine theta. That equals to e to I, 0 times phi, right? So it is already a real function. Okay. So that means we don't need to worry about this zero components. Okay. Right. So now we have a way to form the real functions using the three components of this spherical harmonicas. Okay. And let me summarize this. Okay. Right. So originally we have 1 plus 1, 1, 0, 1 minus 1. Okay. So this one have L squared equals to 2 times h bar squared, and LZ equals to m times h bar. So they are simultaneous eigenstates of L squared and LZ, right? But now let's move this one to the three components. So we have px, and then this is 1, 0, and py. Okay. So this one actually is the real part. This just equals to 1, 0, and this one just equals to y, the imaginary part. Okay, but we still have L squared. equals to 2 times h bar squared. And LC uncertain, okay. So we don't have this states as the eigenstates of LC, okay. But later on, you can see that this Px, Py, and 1, 0 states, they're actually quite interesting, okay. And the point that all of these Px states, 1, 0 states, and the Py states, they are real functions. Okay. So that's good. Okay, so we can plot them. So let's try to look at this in more details. Okay. So let's look at the 1, 0 first. So this one actually is nothing but just cosine theta. Okay. And that's actually, if you write this into the coordinates, so you just see over r. Okay. Right. Very interesting. And if you look at this 1 plus 1 theta phi. Okay. So that actually equals to sin theta. Okay. Divided by square root of 2. Okay. And times ei phi. Okay. So this one equals to 1 over square root of 2. Okay. Sin theta cosine phi plus I sin theta sin phi. So very interesting. This is a real part. This is imaginary part. But this one is just x over r. This one is just y over r, right? So that means this px actually states is just the square root of 2 of the real part of y1 plus 1. So this is nothing but just x over r. Of course, and py just square root of imaginary part of y1 plus 1. That's just y over r. So hence x and y, right? So that's why we call this one x and y components. And of course, so now you can say that let me just call this one PC, right? So that equals to c over r. Okay. So now, so you have this very nice, properties of the p states. I have 3 components, x, y, and z, right? And you can see that now you can say that LZ 1, 0 just equals to 0 times h bar, right? So you can see immediately you just do the matrix, do the permutation of the coordinates. Say, right. So immediately you got the LZ. Sorry. So you can say this one just means LZ PC equal to 0, right? So that means this is eigenstate of LZ. And then by this permutation of coordinates, immediately you can say that Lx acting to Px, that will equals to 0, and Ly and Py equal to 0. So this Px, Py, Pz are actually just 3 components, the eigenstates of the 3 components of angular momentum with eigenvalue 0. Okay, so that is something interesting. So Px, Py, and Pz are just eigenstates of Lx, Ly, Lz with respective eigenvalues 0 h bar. Right, it's very interesting mathematically. And if you look at this one, there are just 3 components, x, y, z, right? Okay, so if you write down this as 3 components, say Px states, Py states, Pz states. So this one is just proportional to x of r, y of r, z of r. They're just like a vector. So 3 components. Actually, if we do a rotation, so if you rotate, you know, x to y, y to z, and z, for example, if we do a rotation, sorry. So if we do rotation, for example, so this is x, this is y, and this is z, right? So if we do a rotation, say, you do a rotation like this one, and change z to x and x to minus z. Okay, and immediately the states 2pz, pz will becomes px, right? Okay, so that means the 3 wave functions, okay, changes to each other on the rotation the same as 3 components of a vector. Okay, so that's why we say that the p states are vector states. Okay, so that's something quite interesting, right? So this is one interesting thing that we learned about this p states, right? How about the radial part? So now this is YLM times the radial part, right? Okay, so that's give us percent MLM. For now we consider p states, of course. Let's consider the lowest p states is 2 p states. So you have 2px, 2py, 2pz. Okay, so basically, so 2px just equals to R21 R times square root of the real part of y1 plus 1, and the 2py just equals to R21 R times the square root of, and then the imaginary part of y1 plus 1, and 2pz just equals to R21 R times y10, right? You know that this one is basically proportional to R21 R times x of r, right? And this one is going to be R21 R times y of r, and this one is going to be R21 R times c of r. That's very interesting, right? So this is the 2px states and 2py and 2pz states. So you can see that it's a radial part times x component. It's radial part times y component. It's radial part times the z component. Okay. So that means once you know this radial part, okay, let's look at the radial part of this r function. Okay. So look at this r. Okay. And this radial part of this function actually is 0 at I equals 0, and then goes to 0. But remember, it just has a 0 point right here, and it has no node. Okay. And of course, so this is R21 R. If we look at the probability of finding the particle at the distance r to r plus dr, so you times r square, and so this one will goes to high order 0, something like this one, right? So this one is just PR that equals to R squared and R21 squared. Okay. So that means, so if you look at the wave function, so if you are interested in the wave function, say per se 2px, right? And then you can plot this one in the x, y, z, right? So you know that this one is polarized in the z component, x component. So you can now plot this one something like this one. So this is x-axis. This is what the z-axis. I know that it's just x times the radial part, and the radial part is 0 right here. So this is 0. So it's 0 right here. Okay. So this is 0 right here. Okay. And then it goes like this. Okay. And it's anti-symmetrical, right? So here you got a minus sign, and here you have the waveform is a plus sign. And along this one, this YZ prime. Okay. So if we plot this one as a, okay, so this prime. Right, so this one is the node surface at the YZ plane. Right. So that's the wave function of the two PX states. Okay, so it has one node surface, and then it's positive on the positive axis and the negative axis. So this is very much like a dipole, right? Okay. It's like a x component of a dipole. Right, there's positive on the right x and the negative on the left x. Okay, and similarly, you can have some other states because they are just the same, right? So 2py. So that will be something like this one. So you can just plot the axis like this. Okay, and then the wave function will go like this. Okay, right. So you have a negative right here and positive sign right here. Okay, and then similarly, you're going to have 2pz states. So that will be also very simple. Okay, and again, there's positive like this one, and then negative like this one, right? This is negative, and this is positive, and then so all of them have so the number of node surface just equals to 1. That equals to actually n minus 1, right? Because n equals to 2 in this case. All right. So this is the 2p states. All right. Let's take a break right here, okay? In case you have some questions about this comparison between the 2p states and the vector components, okay? Just ask your questions. I guess some of you may be slightly confused at this point, right? It's interesting, intriguing, but you know, take you a while to fully appreciate and to fully understand these features of the p states. Okay. Okay. Times R31R, right? Okay, so that is, and this one will give us the angular part, which does not depend on R, right? And this part is the radial part. Okay, so let's look at the radial part first. Okay, so you can see that of course as compared to the 2r, so this is r, and of course it's going to be 0 at this point. Okay, and it's going up, and then there will be one node goes like this. Okay, so you have one node surface right here. Okay, right, and then you of course if you are interested in the if you're interested in the probability of finding the particle at a certain distance to the to that one, that you can actually have a PR that equals to r squared and r31 squared, right? And so the first part is just the radial wave function. Okay. And then again, so we can just multiply this one to the angular part, and then we got the wave functions. Okay, so let's consider per side 2pz, for example, and we look at this as the axis plane, right? So then you have something like this one. So this is x, this is c of right, and then now because you have you have this node, right? So that means somewhere here should be 0. So at this distance, right? So you can say that if you there's one distance, so along this distance, it's going to be 0. Right. But we also know that for the p states, so this one should also equal to 0. Right. So that means if you look at the wave function, it's going to be something like this. Okay. And then you're going to change the sign. Goes like this. Okay. So this one is negative, and this one is positive. Okay. And then here, so you can have something positive, okay, but of course it's going to decay to 0 in the infinite, right? And then this will be, sorry, it should be something like this. Okay. For the lower part is something like this one. It's anti-symmetric. Okay, so you can see that this is positive, this is positive, and this part is negative, and this is negative. So that's the shape of this wave function, right? Goes like this one. Okay. 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 So that's the 2pz states. All right. So this one is so you can see that there will be two nodal surface. This is one. This is another one. Okay. So the number of the nodal surfaces is 2. That equals to m minus 1. So again, right? So you have all of this kind of things. The number of nodal surfaces actually is just m minus 1. No matter it's a p state or s states, right? And how about the 2px, 2py? So it's very simple, right? You just rotate this one to the, for example, you can just say, let me take this. Can I do this? Let me check. Yeah, so you can just do rotation, okay. If you do a rotation of this figure to the, for example, you can do a rotation like this one. Let's do this way. So this is, you can have, say, call this one. This is X, this is Z. So again, you can have, you know, the wave function like this. Okay. Right. So this is the 2p, 3px. Sorry. So this is positive, and then this one is negative. Okay. So you have the nodal surface. So this is one of the nodal surface. Well, on this surface is 0, and this is another nodal surface. Right. So you can see that this is 2px, and similarly for 3py state, right? Okay. Now you can say that this is the case for the 3p states. You can continue this on to the 4p states. Okay. So if you want to go to 4p states, okay. I'll leave them as detail, but I just draw one picture for you. Okay. It's very easy. Let's say 4px, for example. And you know that there will be, let's just plot this surface. So there will be one surface that's 0, another surface that's 0. Okay. And this is surface that's 0. So there will be the number of the nodal surface is 3 equals to m minus 1. And then you can draw the wave function is positive, okay, and then it's something like this one, and then you have something like this one, okay. So that's the positive part, but you can also have the negative part. Okay, so this is the negative part, and this is the positive part. Right. So across any nodal surface, the wave function changes sign. Right. So this is the 4p states, 4px, and easily you can plot this one for the 4py and the 4pz. Okay. Right. Pretty simple to show this. Okay, so the importance of the sign. Okay, I just wait for 1 minute. I will show the importance of this sign. Okay, so if you look at the probability, it's always positive, right? But if we look at the superposition, it will be different. But let's wait for 1 minute. But in all of these cases, you can see that the number of surfaces where the wave function is 0, we call this nodal surfaces. There's always m minus 1, no matter it's S state or P state. Actually, later on you can also see it's the same for the D states, okay? And even for F states, for all the states, you have this kind of things. So the reason that this number of nodal surface actually determines how this wave function is oscillating in the 3-dimensional space. Just like if you consider 1-dimensional case, the number of nodes of a wave function determine how oscillatory is the wave function, right? And that determines the energy, okay? And for this 1 over r potential, so we know that the energy actually is just given by this m, okay? So that means this m will determine how much oscillating this wave function is, okay? So if you fix the energy to be minus Rydberg minus n square over n square, and then you know that to fit into this energy. So the number of oscillations this function could have in the 3D case, the space is actually is fixed. It's always m-1. Okay, so check this one for other states. Okay. So now let's show the example of okay. The importance of phase. We consider the example of dipole transition. And let's consider state. The psi just equals to, for example, 1s plus 2px. Okay, at t equal to 0. So let's look at this state first. So this one, of course, is very simple. It's just a circle, right? Positive. Okay. And for this one, you have two parts. This is positive. But you also have a negative part. So this one is x equal to 0. And this one is x equal to 0, right? And now if you plus these two, so what will be the result? You plus these two, what will be this? So this is psi 1s, this is psi 2px. If you plus these two, what will be? And then you can say that, let's put this one as x equal to 0, right? On the right hand side, you can have, because the wave function, both of them are the positive. So that means you can have a region, the wave function will be enhanced. Okay. But then on the right hand side, at a certain point, you can have a destructive interference, right? So the wave function will be smaller. Okay. Something like this one, right? So this is the case. So you can see that the wave function will be, so because of interference, okay, and because of phase plus and minus of 2px, okay, for plus or minus x, right? You got a non-symmetric probability, right? So that's the case at t equals 0. Now let's let the t to increase, and then psi will equal to 1s e to minus I e1s t over h bar, right? And then plus 2px, that will be e to minus I e2 t over h bar. But this is just e1, okay? And this one can be written as e to minus I e1 t over h bar. Okay, that's a global phase factor. What's inside? Now is 2px e to minus I, let me call this one e2 minus e1, right? T over h bar. Okay. Right, so that's the state. And now this one will introduce a time-dependent phase. Okay. Let's consider a few examples, okay, of the state. Let's consider, for example, the case that t equals to, say, pi over 2 times h bar divided by e2 minus e1, right? So what will be this? So you're going to have E2 minus I, E2 minus E1, and the T over H bar. This is the phase factor, right? So if we put T is over pi over 2 right here, so that way equals to E2 minus I pi over 2. That equals to minus I. Okay? So now let's look at this percent T. That will equal to what? So that's essentially just 1s, because the global phase size is not important. And plus, now this plus will change to be minus I 2px. Okay? So now this is the phase. This one is positive. This one is positive. And this one is negative. But now, because there's minus I, so this will become minus I, this will become plus I. Right? You do the summation of the two. And now you can see that this is going to be plus 1, right? Plus 1 minus I and plus 1 plus I, they're actually the same, okay? Have the same amplitude. So now you got some function like this one. Sorry, this is bad drawing. So this is 1 plus I, so 1 minus I. This is 1 plus I. Right. So you got a symmetric probability distribution, right? Okay. Let's continue this process. What if T equals to pi over H bar over E2 minus E1? Of course, here you still have this one to be plus 1. And now you have this one. They change the sign. Now this one will be minus 1. This will be plus 1. Okay. You do the summation of the two. So that will give us and now you're going to have constructive interference right here and destructive interference right here, okay? So this one is small and this one is big, and this is x equal to 0. Right, again, you got a non-symmetric. Okay, of course you can continue this process. Just continue this. How about T equals to 3 pi over 2 and over H bar divided by E2 minus E1. Okay, you got something like this. This is still plus 1. And now this one has 2 parts, right? But now this is plus I, this is minus I. So the summation of these two will just give us something like this one. This is 1 plus I, this is 1 minus I. Okay, so this is again symmetric probability, okay. And this one is a non-symmetric probability, okay. Of course, you can also consider the case that what about if T equals to 2 pi over H bar over E2 minus E1. And again, you have this one to be plus 1. And now this one you have 2 parts, right? So minus 1, plus 1, and do the summation, give us interference. And again, so this one gives us a big part, and this one gives us the small part. This is x equal to 0, and this is non-symmetric. So now you check the whole process. Okay. Check the whole process. You actually come back, right? Okay. So if we look at the, so you can plot this one as a function of t. Okay. And this one you can look at the position, average position of this state. At t equals 0, because interference, so it's something right here, right? It's something right here, it's positive. And then at t equals to half pi over h bar over E2 minus E1, you have something right here, okay? And then at pi over h bar over the energy difference, it's going to be negative, but it's just the opposite, right? And then 3 pi over 2 is right here, and then 4 pi. 2 pi over 2. 2 pi, okay. So you actually have an oscillation, goes like this one. Okay. So that means xt will equals to, we call this one x21, the matrix element, times cosine omega t. And this omega just equals to E2 minus E1 over h bar. So this is nothing but just the dipole oscillation. Right. So that will induce, okay, emission or absorption of light with the transition 1s between the 2 px. And this light actually should be X polarized. So now you can see that this phase is indeed important. So the phase is, without this phase actually you would not have this kind of interference. Suppose you just say the phase is the same. Okay, it's all positive. You can do this again, you find that there's no such oscillation. Okay, and later on we check the D states and you're going to see that you actually don't have this oscillation. Okay. All right. So that is the case. You know, if you have a superposition of the 1s and 2px states, you actually have a dipole oscillation, and the frequency of this one is just the energy difference divided by h bar, right? So that means the light that will be absorbed or will be emitted will just have the same frequency as this energy difference divided by h bar. Okay, so that is something interesting and important. All right, so that's about the 2p states. So let's look at the D states. In this case, L equals to 2. And then, of course, you can have M equals to 0 or plus minus 1, plus minus 2. So there are 5 components. Okay. For each L, there will be 5 different M. Okay. And again, you know that this, we call this one 2, 0. So this one actually equals to P2, 0 cosine theta and e to I 0 times phi, right? So that's P2, 0 cosine theta. It's already a real function. But the other components, and a lot of very convenient. So for example, you have plus or minus 1, that will equals to P2 plus or minus 1 and the cosine theta and e to plus or minus I phi, right? These are complex functions. They're eigenstates of LC, but they're not real functions, so not very convenient. So, but we can again take the real part or the imaginary part. So let's look at the real part again to make this one to be normalized. So we times square root of 2 right here, and the 2 plus 1. So that actually equals to square root of 2, and you know, this is 2 plus 1 plus 2 minus 1. Okay, so that will equals to P plus minus, sorry, P plus 1, 2 cosine theta times cosine phi. Okay. And this one, so let me write down this one first, okay? And the square root of 2, imaginary part of 2 plus 1, that equals to square root of 2, there's I right here, and 2 plus 1 minus 2 minus 1. that will equals to p plus 1, 2 cosine theta sine phi. I think there's a square root of, let me see, square root of 2, right? Okay, thank you. And there also a larger magnetic quantum number, right? So if m equals to plus 2 and take the real part, that will be 2 plus 1 plus 2 minus 1. Okay, so that will equals to square root of 2 and p 2 and the cosine theta, and now cosine 2 phi. Okay, and you have also this one. So this is 2, sorry. Minus and 2 minus 2. That equals square root of 2 times p2 cosine theta sine 2 phi. Okay. So that's the states, and these are all real functions, right? Okay. For your convenience, let me just take all the states. Associated Legendre functions. Okay. Let me copy it right here. Okay, for your convenience. Actually, p20. That's one thing we need. It's just 3 cosine square theta minus 1 over 2. Okay. And we also need a p21, right? p21 is actually minus 3 cosine theta sine theta, and p22 equals to 3 sine square theta. Okay. So with this one, let's check one by one first. Let's look at this one first. So this 2, 0 actually equals to 2 times 3 cosine square theta minus 1. And this one, if we write in terms of x, y, z, that will be 2 and 3z squared minus r squared divided by r squared. Right. Okay. And how about this term? So this term, if you put this one, you actually find that, so this will be okay. You put this one right here. So that will be minus 3 square root of 2 and cosine theta, sine theta, cosine phi. And this one is just the x component. This is just the z component, right? So this one will give us minus square root of 2 and then times x times c over r squared. Okay. And the imaginary part, 2 plus 1, that equals minus square root of 2 cosine theta, sine phi, that equals minus 3 square root of 2. Y times z over r squared. Okay. And then the square root of 2, I am 2 plus 2, sorry, real part of this 2 equals to 3 sine squared theta times cosine 2 phi. Cosine can be written as cosine squared phi minus sine squared phi. So that will just equal to, okay, r squared, 3x squared minus y squared. And the square root of 2, the imaginary part of this one, okay, 2 plus 2, that will equals to 3 sine squared theta. And the sine phi squared, sine 2 phi, sine phi is just 2 times sine phi and cosine phi. So that will equal to r squared 6 times, I think it's x, y. Right. So this things are probably not properly normalized. Okay. So if you put all of this one together, you can see that there could be just xc, yz, x squared minus y squared, xy, and z squared minus something, right? So then we denoted all of this one as, okay, we call this one dz squared. So this one actually is proportional to 3z squared over r squared minus 1. And then this one, we call this one dxc. So that's just proportional to xc over r squared. And this one, we call this one dyc, of course. So that's just proportional to yc over r squared. And this one, we just call this one dx squared minus y squared. That's proportional to just x squared minus y squared over r squared. And this one, we call this one dxy. That's proportional to r squared and the xy. Right. So they're actually very interesting things. So I'm not sure how much you have learned about electromagnetic dynamic, electromagnetism. How many of you have already taken? Have you taken? Have you taken this one? So if I have taken this one, you know that. Okay, great. So you probably know you have learned point charge, dipole, and then quadrupole. Okay, and so on and so forth, octupole. And then any charge distribution can be written as, so any charge distribution, so if I have a raw charge density, so this one actually can be approximately as, okay, a charge Q over R. So that is, sorry, Q times delta function, right? So this is, you know, it's just a point charge. And then you have a dipole, something like this one. And then you can also have a quadrupole. Okay, something like this. But anyway, so you know that you can expand the charge distribution into a dipole, quadrupole, point charge, octupole. And this one has one component. This one has 3 components. And this one has 5 components. Okay. So this things actually exactly are just the 5 components of a quadrupole. Okay. So that's why we say that the D states, okay, it's 5 components of a quadrupole. Basically, we are saying that they are related to each other on the rotation. The same way as 5 components of a quadrupole do, okay? All right, so that's you can look at this one, and then you can also have a picture, okay? Let's look at, for example, dxy. And dxy, we know that it's xy over y squared, right? Something like this one. So that's a state. And now let's put this in a picture. Let's call this one x-axis. This is y-axis. I know that, and then along this surface, when x equals 0 or y equals 0, there must be 0, right? And then they will be positive if both of this one are positive, or both of x, y are negative. But another way is going to be negative. So this is negative, this is negative. This is positive, this is positive. So you can see that if you have a charge distribution like this one, it will not, the total charge is 0. And then the dipole is 0, but the quadrupole is not 0, okay? So this is one of the quadrupole component, okay? So this is similar to the XY component of a quadrupole. Okay. And similarly, you can also have say dxc, and then the same thing, right? What you need to do is put this x, this is c, and then you have and this one is positive, and this one is negative, and then this one is sorry, this one is negative, this one is negative, 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 positive, positive, right? So that's the wave function, the angular wave function of this one. Okay. So all those x and then look at the xy squared. Okay, let's look at another interesting one. Dx squared minus y squared. So that will be something like this one. Okay. And now along this line, when x squared equals to y squared, so these are the surface that the wave function is 0, right? But along this part and this part, this is positive. And along this part and this part, this is negative, right? So you can see that from this to this is just a rotation, right? Just rotate by 45 degrees, 90 degrees, sorry. 45 degrees. Okay, about the z-axis. Right. You got this one. And from this one to this one, you can also do some rotation, right? You just rotate the xc to the xy, right? So they're all related by rotation, okay? Of course, you can have another one. Okay, you have d, let's say xc. I think there's a yc, right? Is there any yc? I think there's yc, right? So this is just y, and this is c, and you know that. So you're gonna have components like this one. So this one is positive and positive, and this one is negative. Okay. So this is the yc. Okay. So all of this one can be related by the rotation. Okay. So you can go from this one to this one, or you can go from this one to this one. Okay, so just by rotation, okay. But there's another term that cannot be related by the rotation, okay. That's a d z squared. So this one is 3z squared over r squared minus 1, okay. So you can see that this one actually is also very interesting. You did something like this one. So you can see that so this one equals to 0 when 3z squared equals to r squared, right? This is one of the nodal surface, okay? So this wave function will be something like this one. So it's you have a disk right here, okay? And then you have this one. So this one will be negative, this one will be negative, and the middle is positive. And you may wonder, no, this one doesn't look like anything like this one, right? But this one actually can be written as a superposition of. So you can put this one as. Let me just change this one a little bit. You can now understand this one. Now this is 3z squared minus 1 minus r squared over r squared. Actually can be written as r squared z squared minus x squared plus r squared z squared minus y squared, right? So you can see that this one is just can be written as z squared minus x squared plus d z squared minus y squared. So it can be written as something like this. The summation of these two components, okay, have superposition of this one, and then you do a rotation, right? So they are all related, okay? So, but from this to this one, you need a rotation plus a superposition, okay? So you basically you need to have these two components, okay, to form this, okay? So that is the all the 5 components of this states, okay? And then similarly, you can look at the radial part. So that will be M2 R times all of this and ND states, right? Something like this one. Okay. Now, for example, you can consider the case R32, right? So you know that this one must goes like something like this. That's no loss, right? So this is R32. And you can also, if you are interested, you can also look at so this is PR that equals to R squared and R32 squared. Okay, so that's the probability density, for finding a particle, the electron at the distance between R and R plus dr, right? Okay, and then you can check the distribution, and then you're going to have, for example, just show one example. Okay, so let's look at the states, say D 3D. Sorry, this is X, this is Y. Let's look at the state 3D XY. Okay, and you know that so the function will be something like this one. That's very simple, right? Okay, so minus plus. How many? What's the number of node surface? So basically, you need to look at the surfaces, right? So you can see that yes, it's 2. Wonderful. Right, so you can see that there are one surface around here, one surface right here, right? These are the 2 surfaces that are going to have this one to be 0, okay? So this is one of the states. You can try this one for other states, and so you can also read the lecture notes on more states, right? Let's try one more thing, okay? Let's say look at the R4 R, okay? In this case, now the radial part has actually one oscillation that goes like this one. R4 This one goes like this. Okay, and then the probability of another distance. Sorry, that's bad. Okay, so it goes like this one. But anyway, so you know what's this? And then you can see that there's one more radius, right? So basically, if you again plot the states, let's look at the 4DXY. Okay, and you know that now you have a surface like this one that will give you 0, right? Okay, and so this xy axis are also not surfaces. So now you can see that again you have this one, something like this. Okay, but now you have this one is negative again, right? But you have one more thing outside this. Okay. Okay, so this will give us a wave function. You know, for the 4D states. Right. So you have the number of nodes, not a surface. It's 4 minus 1, they equal to 3, right? Okay, so this is one surface. This is one surface. So this is another surface. Well, the wave function is 0. Okay, so you can also draw the 4D states for other things. Okay, right. So I leave that one as some fun for you, so you can continue to play this game and by drawing more and more functions, and also check the internet and to look for more like animations, like 3D plots of this wave function, so that you have a better understanding of such kind of states. Okay. Another importance of phase. Okay, let's consider state. For example, that's 1s plus, say, 3d and xy. Okay, so this function is something like this one, right? But this function is something like this one. So if we even do the summation of this, what do you get? Positive. So you're gonna have positive interference along this direction, right? That's a very bad drawing, sorry about that. Okay, so you're gonna have a positive interference along this direction. Okay, but I have a negative sign, so you have a kind of destructive interference in this diagonal direction. Okay, so this is the case. And then how about after a period that 1/4 of the period, you got to say minus I right here, minus I right here, plus I here, plus I right here. And now one plus I and one minus I, they will have the same amplitude, right? So that will give us something. Okay, it's again very symmetric. Okay, right. You can continue this way. So immediately you can see that in all of this case, x equal to 0 and y equal to 0. Of course, c also equal to 0. Okay, so that means there's no dipole oscillation. That means no transition between 1s and 3D. Okay, so this 3D xy is just one of the states. Actually, you can apply this one to all the other ones. Okay, so but this is just the one a special case of the selection rules in atoms. Okay, so we are not going to discuss the general rules, but this is just one of this one. And you can also check. So I'll leave this one as exercise for you to show that like 2p to 3d is allowed. Okay, again because of the phase. Okay, right. So if we have the transition, have the superposition state of the 2p and the 3d states, you can see that there will be a dipole oscillation as a function of time. Okay, and then you can have emission or absorption of the light. Okay, you can continue this form. Okay, we have tried SPD states, and you can also go to see the F states. The F states actually, okay, F states. So L equal to 3, M equal to 0, plus minus 1, plus minus 2, plus minus 3. There are 7 components, like octuple. Okay. So plot the figures for fun. Okay. And this is another exercise for you. Okay, just try it and just play these wave functions and play this like node surfaces and all of this one. For example, okay, I show one example: x and y. Okay, and they actually have so one of this example, you can have a surface like this one, and then you can have the states goes like this. 1, 2, 3, and then you have okay. And then you can have something like this one. Sorry. I should use different color. Okay. So the question is, this is the, let me ask you, n equal to what? Can anyone answer this question as a quick quiz? N equal to what? So this could be a final examination problem, right? So example question for final examination. Okay. Okay, yes. This is the case that n equal to 5 and L equal to 3. Right, so this one is called dx cubic minus y cubic states. Okay. Right, so you can actually, it's once you get familiar with this kind of this node stuff, actually, you know, you can have a very intuitive pictures of those vector, quadruple, octuple states. We call this one P states, D states, F states, and then you can have G states, H states. Okay, but usually we don't care about those high angular momentum states. Okay. All right, so that's all we have for today. So just let me know if you have questions. Okay.